Okay, so the ratio test is it's up there on one of the most useful convergence tests, very high on the usefulness scale. So so let's say, suppose n equals 1 to infinity. A sub n is such that so let's say we have so the limit. So what we're going to do is we're going to take the limit of the ratio of the sequence. So the limit as n goes to infinity of a sub n plus 1 over a sub n. So if this is less than 1, then the series converges. Not only does it converge, it converges absolutely. That is right. Okay. Now, if the limit as n goes to infinity of a sub n plus 1 over a sub n is equal to L, which is greater than 1, then the series, take a wild guess. Diverges. Absolutely diverges. Okay. And then if the limit as n goes to infinity of a sub n plus 1 over a sub n is equal to 1, then what do you guys think? Excellent idea. So the ratio test is inconclusive. Inconclusive. So we don't know what's happening. Don't know. So we have to use a different test. Okay, so let's see. So we'll do fun times slash proof. Fun times slash proof of the ratio test. We'll prove the first one. The second one's similar. I mean, we'll actually pretty much prove both almost at the same time. But the idea of the proof is basically to compare it with a geometric series. And if you kind of look at it, it makes sense, right? Because so here you have the ratio, right? So if you think of the geometric series, you have this ratio, and then if that ratio is less than 1, then if you're thinking of the geometric series, then it converges, right? If it's greater than 1, it diverges. So we're going to set it up so that, the idea of the proof anyways, is to set it up so that you have this ratio is less than a convergent geometric series, and obviously for the second one it would be greater than a divergent geometric series. Okay? Alright, so the fun times begin. So let's see. So what are our assumptions? So we know that since the limit as n goes to infinity of a sub n plus 1 over a sub n is equal to L, which is less than 1, what does this mean?
It's going to converge.
It, what is it? We use this in the proof of, which one was it? The
double.
Well, yes, but this isn't necessarily what we get. So just from the definition of convergence, remember that since the limit is so it's approaching L, right? So then that means that there's a point where there, let's say that there exists some number R, let's put it in red, such that R is, let me see, hold on. So our sequence is converging to L, right? So then L is less than, R is less than 1. Dun, 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 dun. So R is just some number that's in between L and 1, right? So there's some number. So let's just say this just some magical number, right? So no matter what this number is, doesn't matter what it is, this ratio is going towards L, right? So if you go out far enough, no matter what this number R is, then there's a point where the sequence is going to be in here in between L and R. Does that make sense? Or at least less than R. Yes? Does that kind of make sense? So like let me do this. Let me draw a little number line. Let's say 1 is right here, right? And you have L right here. So this is a number line, right? So you have L is, at least L is less than 1, right? Okay. And then R is somewhere in between L and 1. It doesn't really matter where it is. But the sequence converges to L, right? So this sequence, the ratio. So the sequence can be who knows, over here, over here, over here, over here, over here. But there's a point where, since it has to converge to L, that means that all of the terms of the sequence have to at some point be in between. They have to be less than whatever that number R is, right? Because they have to go towards L. So it can happen after 100 terms, after 1,000,000 terms, after 1,000,000,000,000 terms, but it has to happen that if there's a number right here in between L and 1, then they have to go eventually be less than R, right? Okay, all right, good. So, such that that's true, and let's see, the ratio a sub n plus 1 over a sub n, well, I'll write it down again, is less than R is less than 1 for n greater than or equal to some number m. Right? So what we're saying is this ratio is less than R after that point m. So m, that's when we say after the 100th term or the 1,000,000th term or the trillionth term, that's what we mean by this number m. Yes? Okay. So then notice then that if I just use this right here, so if I take a look at this right here, then I have that a sub m plus 1, the absolute value of a sub m plus 1, is less than what? A sub m times times r, right? Okay. Now, what about if you take a look at the next one? So what about a sub m plus 2?
Less than a sub m plus 1 times r.
It's less than a sub m plus 1 times r, right? But what is a sub m plus 1? A sub m plus 1 from the line before, that's going to be less than a sub m times so here I'm grabbing this one, right? So this is this one from the line before. So a sub m plus 1 is less than a sub m times r, right? And then I have the r that I had earlier, this one right here, right, is still there. So that's equal to a sub m times r squared, right? Right, so a sub m plus 1 is from the line just directly before it is less than a sub m times r. So then I just substitute that, right? The purple. So the purple a sub m plus 1, I replace it with the purple a sub m r. And then there's that r that was already there, right? So then this is, so a sub m plus 2 is less than a sub m times r squared. So if you, again, continue this, you keep doing this, you get that a sub m plus n is less than a sub m times r to the n, right? But what do you know? What do you know about r? R is less than 1, right? So this right here, so this is r is less than 1, right? And since r is less than 1, this on the right side, what is it? What does it define? This defines it's a geometric series, right? So this is a geometric series, right? A convergent geometric series. And your R series is less than that convergent geometric series. So then that means that R series is going to converge, right? Does that make sense? So ours is, the series that we're looking at is a sub n, right? So what we have over here is we've shown that our series, the one that we're looking at, is less than the geometric series. Now, do I worry about this, the fact that I'm only looking at after m? Am I worried about that? Because notice, I showed that the series from m on is going to be less than this geometric series, right? Does that affect the convergence of the series starting at 1? No, right? Remember, we're talking about the tail is what matters, right? So our series, which is on the left side, is less than this convergent geometric series. So that means that our series, this series, converges by the comparison test, right? So really what this directly from here is this series, n equals m to infinity converges, right? But then that also means that n equals this series, a series starting at 1 to infinity also converges, right? And not only that, it converges absolutely, right? Okay. Does that make sense? And so notice that, so suppose R, if R is, you can do something similar to this, but with R greater than 1, right? And so the idea is very similar, except that you would have R is greater than 1, and then your inequalities would be flipped, and then you would be able to show that it's greater than a divergent geometric series, and so then it also diverges. For the second case, right? The second part of it. Very, very similar. Thumbs up? Yeah? Okay. So the ratio test is especially useful when you have factorials. So let's do an example. Because so far we've been a bit dumbfounded when we've had factorials. It's always been a bit of a challenge. But not anymore, because we have the ratio test. So let's take a look. So let's do this one. N factorial over n raised to the n. All right. So pretty much almost every single time you see a factorial, think ratio test. Almost immediately. Okay, so what do I do when I'm doing the ratio test? What do I find? What is it that I was doing? If I go back here, I'm finding the limit as n goes to infinity of the ratio of the sequence, the term, and the one next to it, right? So taking that ratio to infinity and seeing what happens to it. Okay, so I take the limit as n goes to infinity of n plus 1 factorial over n plus 1 to the n plus 1 over n factorial over n to the n. Okay. So this is equal to the limit as n goes to infinity of what? N plus 1 factorial times n to the n over
n plus 1 to the n plus 1 times n factorial.
So n factorial times n plus 1 to the n plus 1. All right, so now what? Now what do I do? Now what do I do? Can I simplify anything? Simply? Easily? What can be simplified? What can I do with the factorials? I can simplify the factorials, right? Because n plus 1 factorial is n plus 1 times n minus 1 times n minus 2, right? And no, so like this right here.
Factorial over 1, right?
Well, no, so this one right here is, the first one is n plus 1, right?
Mm-hmm.
And then the next one is n, and then n minus 1, and then all the way up to 1, right?
Mm-hmm.
But what do you notice about this right here? What is that?
That's n factorial.
That's n factorial, right? So then what can I do with that n factorial in this one? Cancel them out. So what's left over out of the factorials? Just n plus 1 on top, right? So this is equal to the limit. Let me just rewrite it so that I get rid of all that stuff. As n goes to infinity of, so the n plus 1 is left over, right? So I have n plus 1 times n to the n over n plus 1 to the n plus 1. All right. And then? Now what can I do?
Get rid of the plus 1 on the bottom.
yeah, so this n plus 1 I can simplify with one of these, right?
So it just becomes n plus 1 to the n.
Yep.
Okay. Yeah.
So I have, maybe this wasn't such a good one. All right, so then I have the limit as n goes to infinity of n to the n over n plus 1 to the n. All right, now what? What do I do there?
It's like very simple, like inequality to show that it's the denominator is always higher, so it's going to be less than 1.
Well, no, I still need to find the limit. What can we do?
Combine them, n over n plus 1 to the n.
We can't really combine them.
Yeah. We can. They're the same power.
So the oh, is that what you mean?
Yeah, n over n plus 1.
Oh, okay. I was thinking you meant something different. Okay, sorry. So the
Yeah, I see what you're saying.
okay, so we have the limit as n goes to infinity of n over n plus 1 to the n. Okay. And so then what?
It looks kind of geometric to me.
Right. I was thinking it was turning to geometric, but that's not really what we were going towards.
Yeah, I mean, it's not quite geometric, right? Because this has to be constant for it to be geometric. If we wanted to find this limit, what would we do?
How many powers? 9.
Let's start with an alpha.
Infinity over
Let's
infinity.
start with an alpha.
What do we have on the inside of the parentheses? This is
Infinity over
Infinity.
oh yeah, infinity over infinity. So let's say I forget about this. So what is it?
It's
One. Yeah, it's going towards 1, right? So 1 to the infinity, which is
1.
No.
it's indeterminate, right?
We have to put it through a natural law.
Okay, so yeah, so maybe not the best first problem of the day, but oh well. Now we're in it, and we're in it to win it, right? All right, so we can do this. This is no problem. All right, so what we do is we set this equal to y, right? And then we find the limit. The limit. Actually, well, let me move over here to the side because I ran out of room. So we'll find the limit as n goes to infinity of natural log of y, which is the limit as n goes to infinity of, if I get natural log of this, then what can I do with this n on top?
N times the natural log of y.
N times natural log, well no, y is the whole thing, including the exponent. So natural log of n over n plus 1, right? Okay. So, now what? How do you guys remember this? I guess it's good that we're doing this because, so what do? You want to use the L'Hopital's rule, right? So you have to bring this one down, right?
Oh, divided by 1 over n.
We'll just move it down, right? So the n that was on top, you just move it as 1 over n on the denominator, right? So then we use L'Hopital's rule. See, this is a good review problem. And since I see that you guys do not remember, then I guess it's a good problem. All right, so this is the limit as n goes to infinity. So I have the derivative of the top, which is
1 over n plus 1, which is n plus 1 over n.
okay. So n plus 1 over n, sure, times the quotient rule, right, with n over n plus 1. So then I have so derivative of the top, which is 1 times n plus 1 minus n times the derivative of the bottom, which is 1, right?
Yeah.
Over
N squared.
n plus 1 squared over the derivative of 1 over n, which is negative 1 over n squared, right? Okay, so then this is equal to the limit as n goes to infinity of
Wait a second. Oh, never mind.
right? So what's going on here?
Cancel out one of the n plus 1s.
Okay, so one of the n plus 1s.
Okay, bring the n squared up to the top. Cross cancel out one of the n's.
So we end up with
Negative.
negative n squared, right? Over n squared plus n.
You can cancel out with one of the n's from go up the line. You got the n denominator there. You bring the n squared up to the top. It'll cancel out that other n, right? So it'll be n over n plus 1, or negative n over n plus 1.
What is it? Wait, what?
Okay, see where you crossed out the n plus 1 over n. You crossed out n plus 1. Bring up the so the denominator there we've got the negative 1 over n squared. Bring up the n squared to the numerator, top line, and shouldn't that cancel out with the n squared should cancel out with one of the n's, that n there? Oh, it is so this free on the algebra.
Oh, I see. It doesn't really matter. I mean, yes, you can, but at this point it's the same, right? Because what is that equal to?
Negative 1 minus n squared over n.
Yeah, this is negative, just negative 1, right?
Mm-hmm.
Okay. So what does that tell me? That's the limit of natural log of y. So then the limit of y is equal to, no, a little more. Okay, a little bit more. So okay. All right, so this is the limit as n goes to infinity of so this is equal to negative 1, right? So then,
Equals negative 1?
what is it?
That limit equals negative 1?
Yeah, the limit as n goes to infinity of natural log of y is equal to negative 1. So the limit as n goes to infinity of y, which is equal to the limit as n goes to infinity of y is equal to e to the natural log of y, right? So this is equal to e to the negative 1, right? Now there was an easier way. Let's see. Let's see if you guys recognize it. So let's go back here to this one. It is something that you should all know, so I guess it's good to point it out. This right here, let's make a little side box here. Let's see. N over n plus 1. This is equal to n plus 1 over n to the negative 1, right?
Mm-hmm.
Yeah? And this is equal to 1 plus 1 over n to the negative 1, right?
Uh-huh.
Yes? Okay. So then if you do that, so if instead of, so then you have this is equal to the limit as n goes to infinity of, I'm going to replace this in the parentheses with what I just wrote down. So 1 plus 1 over n. And then this negative 1, I'm going to put it, not right there, I'm going to put it on the outside. So over here, negative 1. And then I'm going to put the n right there. What is that? Everything except for that raised to the negative 1. What is that?
1 raised to the infinity raised to the negative
Let's
1.
go 0.
This right there, what is that?
Oh, that,
1 raised to infinity.
Right.
It is the definition of E. That's the definition of E. Right there. That's equal to
Really?
E. The limit as n goes to infinity of 1 plus 1 over n raised to the n. That's equal to the number E. So then that's just equal to e to the negative 1, which is exactly what we got when we did all of that. Yes, you are supposed to know the definition of E. You should have seen it, let's see, in pre-calculus, and then again in calculus, and then now here. So so I guess although it was more challenging as a first problem than initially intended, it brought back a lot of good things because it brought back L'Hopital's rule and the quotient rule and the definition of E, which are all, very important things. Questions? No. You guys want another example? I think for the first time you guys liked the proof better than the example. All right, let's see. How about, maybe I shouldn't do that one. I have another one, but I think I'll do a different one first. Okay, let's say we've got the series n equals 1 to infinity of n squared e to the negative n squared. All right, so I don't really want to say that we're only doing the ratio test, so let's leave all options open. So what's the first thing that comes to mind?
Rewrite as n squared over e to the n squared.
Okay, that's a good idea. So n squared over e to the n squared. Okay. And what do you think about that? Can we use the divergence test? Does it diverge? Upon a close inspection, quick inspection of the sequence, n squared over e to the n squared goes to 0 or does not go to 0?
0.
No, I'd say it's not going to 0.
How would you figure out if it's going to 0?
Because the denominator is bigger. But it's not an exponent.
But if you were going to actually find, you would find the limit, right? As n goes to infinity,
Yeah.
right? It's infinity over infinity. So then you would use L'Hopital's rule. What happens if you use L'Hopital's rule? What happens to the top?
2n over e to the 2n over e to the n
2n over e, and then you do it again. So the denominator stays, the numerator goes, which means that it's going to go to 0, right? Okay, so it might converge, right? So doesn't diverge by the divergence test. So, okay, so we're in the maybe converges mode. So let's try the ratio test. So we'll try the ratio test just for fun, see what happens. So we take the limit as n goes to infinity of n plus 1 squared over e to the n plus 1 squared. And then I'll invert and multiply on the same line so that we don't have to write it down again. So e to the n squared ends up on top, and then n squared ends up on the bottom, right? So it's a to the n plus 1 over a sub n. So what can I do to simplify this? So the e's, right? What happens with the e's? So let's say I rewrite this one. This is e to the, if I square the exponent, this is going to be e to the n squared, right?
Mm-hmm.
Plus
2n plus 1.
plus 2n plus 1, right?
Mm-hmm.
So the e to the n squared is going to cancel with the e to the n squared on top, right?
Mm-hmm.
So e to the n squared and e to the n squared. So what's left over as far as the e's are concerned? You're going to have e to the 2n plus 1. And then on top you have n plus 1 squared and then n squared, right? And so what is that equal to? What happens?
Plus 1 over, same thing like we do with the e's.
Well, you can, but so at these you can't simplify, right? The n's really, but you have the highest power of n on the numerator and the highest power of n on the denominator is n squared, right? But then on top of that you have this e, right? So that one's the dominant term, right? So where is it going to? What's going to infinity?
The e term.
Yeah, the e term is going to infinity, right? So these right here are basically, going towards 1, right?
Mm-hmm.
But this one is going towards, so this is approaching 1. But the e, the exponential, is going towards, this is going towards infinity, right? So then the whole thing is going towards
0.
0. All right, so what does that mean? What does the ratio test tell you?
It's going to diverge.
0 is less than
Oh, it converges.
1, right? So it
Yeah.
converges.
Absolutely.
Converges. Absolutely, right? But we'll just say it converges because it's always positive anyways. Converges by the ratio test. Thumbs up? Yeah? Let's see. Alright. One more example. Let's see. I promised an easy factorial, and then I gave you a hard factorial. So let's see. Oh, shoot. Promised an easy factorial, and I gave you a hard factorial. That's just mean. It's messed up. All right, let's do n factorial over e to the n cubed. All right. So with factorials, we're kind of we have some difficulty, right? Because we can't get the derivative of it, and so it's always difficult to just see it. But luckily the ratio test is very, very good at dealing with factorials. So let's do the ratio test. All right, so the ratio test tells us, hey, mister, find the limit as n goes to infinity of, what would I have?
N plus 1 factorial
N plus 1 factorial
over e to the n cubed plus 1.
E to the n plus 1 cubed, right? Okay, times
E to the n cubed
e to the n cubed
over n factorial.
Okay. So then this is equal to the limit as n goes to infinity of, so let's see, what can I simplify? The n plus 1 factorial and the n factorial, what does that turn into? Just n plus 1 on top, right? And then the e to the n cubed over e to the n plus 1 cubed. So let me, down here, let's write down, what does this turn into? This is e to the n cubed plus, what is that equal to?
No.
3n squared plus 3n plus 1, right? So then what happens with the e to the n cubes?
Those cancel.
So the e to the n cubes, right? So the only thing that's left over is all this e to all that stuff, right? So e to the 3n squared plus 3n plus 1, right? Yeah? So what's that equal to? That's easy, right? What does it converge to? Infinity over infinity, but the exponential is much more dominant, right? If you really want to, you can use L'Hopital's rule, but I mean, it's pretty obvious, right? If you do L'Hopital's rule once, you get 1 over, the exponential stays there. So this is definitely going to be equal to 0, which is less than 1. So this sequence converges. Converges by the ratio test. Does this look familiar? Do you guys remember when we did one similar to this one? No. Remember we looked at the factorial compared to the exponential function. Remember? Was that in when we were doing sequences? Yeah, right. What did we say? Factorial dominated, right? But right here, this converges, which means that the exponential dominates. How come? What's the difference between the other one that we did? Yeah. This isn't just a regular exponential, right? This is e raised to the n cubed, not e raised to the n. If this would have been, so notice if the cube wouldn't have been there, notice what would have happened is, so imagine this cubed isn't there, then this would be gone, right? And what would this turn into? Just e, right?
Yeah.
This wouldn't be here. So then what would happen? It would, yeah, this would diverge, right? Which makes sense, right? Because there, in this case, the factorial would dominate. But if this is not just an exponential, but an exponential raised to another power then, came fighting back, wants its title back of the dominant. Yeah.
The factorials, you cancel the one factorial out, and then n factorial cancels the factorial.
Well, because it's what this is. Remember, this is n plus 1 times n factorial. So really, what we're canceling is really this n factorial with that n factorial, and what's left over is just the n plus 1. What else? So I think I'll leave the root test. The root test is very similar to the ratio test. We're not even going to prove it. It's one of your homework problems for next time because it's very similar. So, and then we'll start. So next time we'll start doing the root test real quick, and then we'll do power series, which are a great time. You will love, and as usual.